Good afternoon, everyone. Welcome back to our OpenSPR Pro series. My name is Hawa Gyamfi, and I am a customer success scientist here at Nicoya. Today, I'm going to present to you a webinar entitled Troubleshooting Your OpenSPR Data. Before I begin, I would like to say thank you for making time for this presentation, given the circumstances that we find ourselves in. And I know that we are all doing well. Let's begin. Like I mentioned, today's talk is entitled Troubleshooting Your OpenSPR Data. It's actually a continuation of series 1, 2, and 3. So I'm going to start by giving you a brief preview of what was discussed, and then we will take it from there. So previously, Dr. Piazza introduced us to how to run our experiment and then get the data. And then finally, he came back to also actually tell us how to set up your instrument properly. So that brings me to the start of my talk. So, like I said previously, we learned how to set up the ligand and then inject the analyte and then run the experiment itself. And then after we get the experimental data, we are able to massage it in TraceDrawer and then bring it to a publication quality form. However, this may not be the situation that all of us face. Sometimes we don't get the desired data. Hence, the need for today's talk. This brings me to my outline for today. Today, we will be looking and trying to understand what is happening to our experiment, why we are not getting the desired data. And we are looking at it under these three categories. First, we are going to discuss our problems under non-specific binding or bulk shift or air spikes. And after we identify these, we try to find solutions to them. The solutions that we are going to try to use are going to be sample properties, buffer component, and the experimental setup, ranging from right at the beginning of the experiment, just as how you set up and collect the references, to some maintenance tips. So let's get rolling. We are going to start with non-specific binding. So what is the term non-specific binding? And I'm going to call it NSB for the rest of the talk. As the name implies, is the binding of analyte molecule to undesirable surfaces or undesirable spot on the sensor. So in this situation that we are seeing here, the analyte is expected to bind in the binding pocket here. This makes a very good example, but then it finds itself on the sensor surface. Why do we have to control this? We know that SPR relies a lot on the mass that is reaching the sensor surface. Then it's relayed it as the response that we see on our screen. So if you have these false masses reaching the sensor surface, the detector is not going to be able to distinguish or separate between this mass and the one that is actually sitting on the binding pocket. So then it gives us false positive responses, and that's why it's very critical to control NSB. Given that we don't see this picture in our sensogram, we would have to educate ourselves, as some of you would know, how to identify these non-specific binding pattern. So Nicoya has actually, it will depend. How you see the non-specific binding will depend on the kind of instrument you have. Nicoya has two kinds of OpenSPR instrument. We have the one-channel system and the two-channel system. The figure here actually is coming from a two-channel system. As the name implies, there are two channels. The channel 1 is dedicated as our reference channel, also called the non-specific binding channel. Channel 2 is the specific binding channel, where one actually would localize the ligand and then watch for the specific interaction between the ligand and then the analyte. So we see from this sensogram that the non-specific binding response is in red. The non-specific binding is in red, and the blue, which is the specific binding, is the specific binding. The actual binding response that we get from this curve is the teal line, which actually tells us that there's actually no specific binding because of the magnitude of the non-specific binding. So in a two-channel system, it becomes easy to identify because you have a channel that is dedicated for the non-specific binding. However, when one has a one-channel system, there's not going to be this blue line. There's just one line. So how do you identify this non-specific binding in one channel? You set up a non-specific binding test. And that's what I'm talking about in the next slide. So if one decides to set up a non-specific binding test, it could be done in a variety of ways. So these are two of them that I have chose to present on. You could decide to go with an untreated surface. So you have a sensor, you don't do all the cleaning and activation, just go ahead and then inject the analyte. Or one could decide to activate the sensor surface, but then does not inject ligand. So in this test, there's not going to be any ligand immobilization, just the sensor, and then we are going to watch how the analyte is attracted to the sensor surface. So the next thing is inject the analyte at its highest concentration that you would be using in your kinetics. Why do we do this? Because you want to get as much signal as possible so that you can identify this NSB. So after the analyte injection to the sensor surface, remember there's no ligand here. We don't expect any binding, any specific binding. But then we look out for any binding. If you don't have NSB, then it means you are not going to see any binding. But then if one has NSB in that particular setup, there would be a positive signal. And this is the time that we would have to go back and then optimize the experimental conditions to overcome this NSB. So you are going to keep playing around the experimental condition until the non-specific binding has been sufficiently reduced. After you get it low to a desired magnitude, then you could use that same optimization to run the remaining experiment. So now we know how to run NSB, or how to actually identify NSB on both a one-channel system and a two-channel system. So what comes next is how to combat it. So NSB, as I said, is binding of analyte molecules to undesirable target surface of the sensor. So if we are able to disrupt the forces that stabilize these analytes on the sensor surface, then we wouldn't have any issues with NSB. So then what forces are there? It depends on the system that you are studying. The forces could range from anywhere from electrostatic to protein-protein interactions. And to combat it, you could play around the buffer pH. You could use blocking molecules, and you could go all the way to even add surfactants. And I'm going to take each of these points and then explain it in further steps. For the purpose of today's conversation, we are going to focus on carboxyl sensor to make it easy to follow. So this is the chemistry that we are focusing on today. We know that carboxyl sensor has COOH on the surface, which is going to be activated to form the NHS ester. NHS ester, being a good living group, would allow the incoming ligand, as we see here, to couple to the activated sensor surface through its primary amines. So basically, this is what is happening. And we are going to study how we could overcome NSB when we decide to go for this sensor chemistry. Bear in mind that a similar technique could be applied to other chemistries. So how do we use the buffer to actually overcome NSB? We know buffers, their job is to regulate the pH of the buffer's then is to be able to resist changes in pH, right? So we are going to take advantage of the pH, trying to play around the pH to hopefully reduce NSB. So, and also adjusting the pH, we know that you are able to regulate the overall charges of the biomolecules in solution. And then since this carboxy chemistry actually relies on charge-to-charge interaction, then it means the buffer will play a very critical role here. So for instance, if one is performing a non-specific binding test or an experiment with a carboxyl sensor, and then has a buffer system in which his or her analyte PI is actually smaller than the pH of the buffer, what happens is that if the analyte PI is smaller than the pH of the buffer is smaller than the analyte, what happens is that the analyte it stays positively charged. It's the same as the proton on proton off event. And conversely, if you have the reverse happening, the analyte becomes positively charged here. And that is what is shown here. If the buffer condition causes the analyte to be negatively charged, what we see here is there's a negative charge on the surface which is going to repel the analyte. However, if you have the situation whereby the analyte has been positively charged, you get the analyte attracted to the sensor surface. That is going to cause a lot of NSP, as seen here on the right. So when we performed a similar experiment in our lab using a protein A IgG binding system on a carboxyl sensor, we tried to study these interactions at two different pHs to see how the pH would affect the will reduce the non-specific binding. What we found was that at pH 6, there was a lot of NSP in all the different concentrations that were used. However, when the pH was increased to 7.4, as seen here, when the pH was increased to 7.4, that's this situation, the NSP was reduced to baseline. So at this point, we know that yes, indeed, pH plays a critical role in reducing NSP. Let's move on to the second item on the list, which is ionic strength. So how does ionic strength actually reduce NSP? I'm going to relate this to chromatography. Even though this technique actually uses an immobilized ligand, the same charge shielding that sodium chloride perform in size exclusion chromatography is very similar to what is happening here. So when there is significant ionic strength in solution based on how much sodium chloride or the salt is in the buffer, what we see is that there would be reduction in non-specific protein-protein interaction as well as non-specific protein surface interaction, which is the one that I'm mostly talking about. So here we see that ionic strength is serving a double duty here. Not only do we reduce interaction to the denser surface, we also reduce interaction to other part of the immobilized ligand, which is not the active site. So doing this experimentally, this is what is observed. Now we are going to only vary the amount of salt in solution. If you have an experimental setup at pH 6 for two different experiments, bear in mind that the only variation here is going to be salt. So experiment A in red has no salt, and experiment B, the buffer was supplanted with 200 millimolar sodium chloride. We see that the buffer with 200 millimolar sodium chloride shows no NSP, meaning that NSP has been suppressed when the sodium chloride solution was increased. So now we have not only pH, we also know that ionic strength could also reduce NSP significantly. That actually brings me to the third item, which is blocking agent. Blocking agent actually comes in several varieties. One could choose from protein blockers, which the popular one we know is BSA. There's also casein and then fish gelatin. There's also polymer-based blockers, which could span anywhere from PEG, PMA, PAMA, and others. And then there's other compound, which could be ethylene diamine, ethanol diamine, and many others. The choice, again, will be dependent on your binding system. So, why do we care about these blocking molecules? Blocking molecules are important in reducing crowding at the surface of the sensor. As shown in this figure, on a carboxyl sensor that has been activated to introduce a ligand in blue here, if there is a site that the NHS ester wasn't replaced by the incoming ligand, maybe there is a limited amount of ligand on the surface, it could be useful because a blocker molecule could actually sit in that location. If you are here and thinking that why shouldn't you add more ligand? Because the more the ligand, the higher your the signal. Yes, you are not far from correct, because you need more ligand, of course, but we have to bear in mind that these molecules that we are studying, both the ligand and the analyte, they are not rigid sphere. They tumble around in solution. So giving them enough space for them to actually tumble and wiggle in solution would actually enhance the kinetics. So then it tells us that it's good to have higher immobilization level, but sometimes if you have more, you could run into steric problem, which could actually decrease your kinetics that you want to observe. And then the second duty that this blocking molecule could serve is that they are able to mimic the ligand density in both channels, like to make sure that both channels have the same ligand. Why am I saying this? In our two-channel system, we advise that the ligand only goes into channel 2. Since the channel 1 is your reference, you don't need any binding to occur in the channel 1 and when we have all the right conditions set. So if after all the ligand immobilization, one would end up with a sensor surface whereby in channel 2 there is one layer of thickness because there's a ligand in channel 2 and there's no ligand in channel 1 because all the other injections go into channel 1 and 2 except the ligand immobilization step. So it means that for some reason channel 1 and 2 are not at the same thickness level, if that makes sense to you. So what one could do is that one could inject a blocking molecule, it could be a blocking protein or something, into channel 1 to make sure that both the channels have the same densities on the surface. And this becomes very important when dealing with small ligands because you don't want to run into issues with sensitivities and bulk effect. I'm going to talk about bulk effect very soon. So I show you examples of what kind of molecules, depending on the chemistry that you are using here, that you could immobilize onto channel 1 to actually match the sensor surface. So now we know that these molecules serve 2 duties already. Let's look at the 3rd duty that they are useful for. So, and for me, it's one of the most important ones, is that it preserves the amount of analyte that one wants to inject or ligand that one wants to inject onto the sensor surface. We know that when we are doing these SPR experiments, we work at very low concentrations. And what happens to biomolecules at low concentrations is that they tend to stick into the vials that they are kept or into the fluidic lines. So putting a blocker molecule would actually decrease these loss to the reaction containers as well as the fluidic lines. And why do we care? Because if you look at a typical sensogram, the association phase here is concentration dependent. So if in your design, you would want to inject 33 nanomolar, you want 33 nanomolar to get to the surface of the sensor because it's going to skew your Ka or the equilibrium dissociation constant. Let's say you wanted to inject 33 nanomolar and for some reason due to loss to vials or to the fluidic line itself, you ended up injecting just 50% of what is anticipated. You see that the Kas are different and the equilibrium dissociation constants are different. So we don't want this to happen. That's why we could also use blocker molecules. And BSA plays a very important role in dealing with this. So let's see how it works to actually regulate the analyte or ligand concentration. So We know that BSA is an escort protein in the serum. This is the same chemistry it will do to your OpenSPR samples. If you add BSA to your run buffer, it's able to maintain the concentration by cutting down the protein surface interaction, and also it will cut down the non-specific binding as we see here. So like I mentioned, BSA is an escort protein. Depending on the buffer system that one uses, the BSA is negatively charged. And the negative charge would actually shield the positive charge of the analyte and guide it until it reaches the sensor surface to prevent non-specific binding, as well as to prevent specific binding binding to the fluidic lines. On the left, I show you how if you are using less amount of BSA, you may run into less coverage, and then you would see some non-specific binding, as shown here on the right. So in the same protein AIGG experiment, if one uses lower percent of BSA, like less than 0.1% BSA, in red, we see some. Oh, sorry. In this case, actually, there was a buffer system that didn't have BSA at all in red, and then a buffer system that contains 1% BSA. And then we see that the 1% BSA actually showed very significant decrease in NSP. So that said, now we have three things to consider. We could use pH, ionic strength, or blocking molecules. But the blocking molecules come in varieties. Which one would we choose? Like I said, is dependent on the system that you are studying. You could choose from protein blockers to polymer-based blockers or other molecules. To help you decide or choose whatever blocking molecules that you are going to use, I'm presenting to you these four rules. There may be more, and like I said, it's solely dependent on your binding system. But then these are things that you could look for. So, like I said, the blocking molecule should be able to reduce non-specific binding, because that is its job at the first place. Non-specific surface protein interaction. And it should also reduce non-specific protein-protein interaction. So it looks like most of my talk has been focused on non-specific protein sensor interaction. But another thing that we could also take a look at is non-specific protein-protein interaction, because the analyte could actually bind to a side on the immobilized ligand that is not the active site. So then that would also cause a lot of NSP. So if you choose the right kind of blocking molecules, you could actually direct the analyte to the desired binding pocket. And the third item, which I think should be number 1 on the list, but somehow I ended up putting it in number 3, is it shouldn't compete with the actual binding that you want to study. So we know that you have a ligand on the surface that is going to interact with an analyte. And you are going to try to reduce NSP by using the blocking molecule, either in your buffer solution or just using it in some form to block in channel 1. So let's say if you have some BSA in your solution, it shouldn't in any way interfere with your binding kinases. That's one thing you have to bear in mind, or anything you decide to shoot. Similar, number 4, similar to every kind of experimental setup, if you decide to go for a particular blocking molecule as an additive in your buffer, let's say if you decide to use, say, 0.05% twin in your buffer, and then you get NSP to be reduced to like 80%. If you come back tomorrow or next year to perform the same experiment, you should get the same amount of reduction. That's what all scientists want. So now that we know that these blocking molecules are useful, let's look at the 4th item on the list, which is surfactant, which are also surface active ingredients. I present to you my cartoon drawing of a surfactant with a polar head group that aids aqueous solubility and a nonpolar tail group that would help solubility in non-aqueous solvent. Putting these two groups together make the surfactant molecule a powerhouse to disrupt both hydrophobic and anionic NSP. For example, if one put twin in the buffer, like 0.05% twin in the reaction buffer, we see here on the top that there isn't no significant decrease in NSP. So what went wrong? That brings me to my bottom curve. We find out that the addition of 1% BSA to the same graph that is up there, if the experiment was reconducted with addition of 1% BSA to the twin in solution, the NSP in black is significantly reduced. The take home from this experiment is that sometimes just one particular additive may not be sufficient in compacting the NSP that you are seeing, but you could use a combination of these things that I have discussed. That brings me to a summary. I would like to draw attention to this equation that I put here, that the response that we see on our computer is a combination of specific binding, non-specific binding, and any bulk refractive index, which we are actually getting to soon. And one should make effort to reduce these two terms in order to actually get the data that would be the publication quality that we want. So, and then I summarize again the combination of different additives, like all the four techniques, and even others that I haven't covered here: pH, sodium chloride, surfactant, and then blocking molecule, could actually help reduce NSP. Sometimes one particular approach would be sufficient. If that is the only forces that is in your system, it's gonna eradicate it. But then we find out that sometimes the combination is needed. I can't end by not indicating that sometimes all of these four things that I have introduced may not work for your binding system, because sometimes you see that changing the pH so much would actually cause the interaction that we are studying to fail, because you cannot just play around the pH in a specific enzymatic reaction or a binding reaction. So what I would suggest in that case is that if you cannot get any of those additives to work, what one would have to do is to try and enhance the specific binding. So what I mean by this is that, let's say you actually optimize your experiment in such a way that your specific binding is so high that the NSP that you are seeing is insignificant. Like you see that it's like 20% of the overall response or lower, then you don't care about it. So that's another thing that we could bear in mind. So then that brings me to the second part of my presentation that talks about, now we are able to reduce the NSP here. So we are left with bulk refractive index, almost there. So how do we overcome bulk refractive index? By the way, what is bulk refractive index or bulk shift? It has different names. Some people also call it DMSO effect. Basically, what this means is that if you have an experiment whereby your system buffer has a refractive index of X, and the injection of an analyte or a ligand causes the refractive index to change from X to X minus 1. This difference of refractive index that is closer to the sensor surface that we are seeing would cause bulk shift. And how do they look like? These bulk shift would be characterized by sharp increase or decrease in responses, as shown in the figure below. For one instance, there is a positive bulk shift where we see that the signal rises, there is no clear binding because everything drops back to baseline again. And the reverse actually happened in another instance. On the right, though, it happened when one tries to study a binding system whereby the analyte itself doesn't cause the bulk shift, but the addition of a competitor causes this kind of pattern of bulk shift in the sensograms. Now that we know how to identify these bulk shifts, how do we control it? We control bulk shift by buffer matching, because I said it usually happens when, let's say, a system buffer of X becomes X minus 1, like it's experiencing some solution that has a buffer of X minus 1. So what do? You dissolve your analyte into buffer X, and then there wouldn't be any problem. However, we find that sometimes it's not possible. And we are so lucky that we have a 2-channel system that would have, we may see the bulk effect in channel 1. That causes a funky pattern in your specific binding as seen here. So that if we correct it, like the overall channel 2 minus channel 1 becomes this. So somehow the software in the 2-channel system has been able to correct for this solvent effect. However, if your effect doesn't get corrected into somewhat usual sensogram, what you could do is that you could take the response of the buffer, like the buffer that the sample is coming in, and just record it by itself, no analyte, just check the response, and then import that response curve into trace drawer, then use it in a solvent correction form to actually resolve this issue. For more information about this, kindly go back to webinar number 2, whereby Dr. Piazza actually shows you on screen how this is done. So now that we know how bulk shift is and know how to correct it, we should be able to actually get specific binding only in our equation. Yay! However, nature doesn't work the way we expect all the time. Sometimes we still can't see the data. We cannot even think of fitting. So what do? We look for things like this. Are you seeing up and down responses that has a lot of signal, like a lot of RE, let's say greater than 100 RUs? Then what may be happening is that you may have collected the reference. So you are going to go back to the right beginning of the experiment, whereby one collects the reference. So if when you are collecting the reference, you don't want to use a sensor that has any gold on it, like seen here. So we X out this. Or a sensor like that, where you get from a previous run, you still have those gold line. What we want is a blank chip, no gold at all. And to get this blank chip, you could just use isopropanol and wipe off this gold and then get a blank chip. Or use a blank chip that came with your instruments. What about if you have peaks that result from buffer injections? We encourage you to do buffer injection during your analyte injection, so that you are able to tell whatever association that you are seeing is not something that is coming from the buffer, but it's the real result of the interaction that is happening at the sensor surface. So for example, in this graph, we see that initially injections of buffer causes a little bit of bump that could be ignored. But here we see that the buffer injection caused a very significant change in RU. What could be happening in this situation is that there could have been a leftover residual amount of analyte in the loop that is actually carried over during these buffer injections. And what I will suggest in that situation is to do cleaning of your sample. Use the proper injection techniques that Dr. Piazza introduced you to the previous seminar number 3. So again, you could go back and look at that seminar and then look for like the instructions, or we also have it in our manual. And then one thing I would also encourage is to do a cleaning, because it looks like the buffer the analyte is sticking around. Not only may it be in your sample loop, it could be somewhere in the fluidic line. So we would want to do a cleaning. I want to also bring to your attention that I know some of you know that already. The cleaning protocol is actually built into our software. You could choose between a basic and then advanced cleaning. And then there's a third cleaning also. We recommend that one does basic instrument clean weekly or bi-weekly. However, depending on the type of system that you are using, your buffer system, let's say if your buffer contains a lot of DMSO, which tends to stick around a lot, or BSA, we recommend that instead of doing a basic cleaning weekly or bi-weekly, go for advanced cleaning weekly or bi-weekly. So let's say you don't have this situation, but then somehow as you do your run, your baseline never stabilizes. It's okay for the baseline to shift around at the beginning of your experiment, but it has to stabilize during the course of the experiment. If it never stabilizes, then it's time for you to clean the instrument. And then it has the same explanation as I give. The type of cleaning you would choose depends on what you are constantly injecting and how severe this contamination is. What about air spikes? Air spikes actually could happen in the beginning of your experiment as seen here, which means that there is an airspace when you were loading your sample. Again, I would actually recommend you to look at webinar number 3 for more details about how to properly load a sample into the sample loop. The second situation is when the air spikes are not at the beginning of the injection, but then they are in the middle or somewhere during your run. What this says is that you may be loading the sample too quickly, or the system buffer that you are using needs some degassing. It's a good practice to keep to degas all your OpenSPR buffer, because we don't only want to get rid of air spikes or air gaps, but we want to preserve the life of our pumps. Finally, I would like to conclude by saying that it's okay for you to see these artifacts, but we have a solution, which is if you happen to see this, you could use experimental conditions or sample properties, or go back to set the instrument, do the instrument setup correctly. And I cannot stress enough on instrument maintenance. Not only would it give you the good data that you want, it would also save you money. We know that we don't want to break those pumps on the instrument, so we would want to do regular maintenance and cleaning protocols to actually help extend the life of these pumps. So with this, I would end, but I want to say that if you're still having issues, and I didn't talk about the problem that you are facing, feel free to contact us at our support page, and then a specialist will be there to help you. I would say happy researching, and then I will welcome your comment. Feel free to type away. Thank you. Are there any comments, any questions, anything that needs clarification? You are welcome. Thank you for coming, and thank you for staying. I'm gonna give it about 2 minutes, and then we will see if we have some more comments. Or again, you could email us on any part of this presentation or the previous ones that needs clarification, and then we will get to you with answers. Okay, so for the hydrophobic type of senses, again, you are going to try to decrease the non-specific hydrophobic binding. That is not the one that you are interested in between your analyte and then your target molecule. So then we are going to actually, if you would like to get more focus on that, you could suggest for us to make webinar on specific senses, and then we could dive more into those chemistries. Okay, so if there are no more questions, I'm going to end the screen, and again, I'm going to thank you for your time and attention, and we will be back soon with another episode of this presentation. Bye for now.